Algebra 1, number 5.4c, we're talking scientific notation and word problems. So we've got a word problem here, and we're going to figure out how to solve it because it seems very confusing. Light traveling from the sun at about 3.0 times 10 to the 5th kilometers per second takes about 5.0 times 10 to the 2nd power seconds to reach Earth. Approximately, what is the distance written in scientific notation from the sun to the Earth? All right, so what are they asking us to find? They're asking us to find the distance from the sun to the Earth, but they want it written in scientific notation. Now, it seems really confusing how we're going to solve this. What kind of equation are we going to write? So we see that right away it says it's about that much, so we know we're going to use an approximate symbol, okay? So we have to analyze this before digging right in, okay? And because it does seem confusing, let's use the strategy, solve a simpler problem, okay? So it's saying the light travels from the sun at this speed per second, and it takes this speed per second to reach the Earth. Now we need to find the distance. All right, so what if it was a car? Let's make it a simpler problem by turning it into a car going slower, okay, using regular numbers. What if a car traveling 3 miles per hour took 5 hours to get home? Well, if it's going 3 miles per hour and it took 5 hours, we're going to multiply 3 times 5 to find the distance of miles traveled. So we're going to multiply our scientific notation. See, if we have a car and it's going 3 miles every hour, how many miles away did it go? It went 15 miles. It went 3 each hour for the 5 hours. So we're going to multiply, just like we did the 3 times 5, we're going to multiply this times this, okay? So what we do is we separate the multipliers from the powers of 10. So we're going to take the 3 and the 5 away and separate them from these powers of 10, okay? And we know 3 times 5 is 15, and because of the multiplication property of inequalities, we can add these exponents because the bases are the same. So we get 5 plus 2. So we know that's 10 to the 7th power. But our problem is only 1 digit's allowed in front of the decimal point, not 2 like a 15. So we need to put the decimal point in between the 1 and the 5. And because we're making the 15 smaller, we need our power of 10 to be greater in order to make it equal. So we move the decimal point here, and now it's 10 to the 8th power instead of 7th. See? Okay? Let's try another one, all right? If there's 10 to the 9th power possible Social Security numbers out of all the possible Social Security numbers, because they're 10 digits long, there's 10 to the 9th power possible different Social Security numbers. And the population of the United States is 3 times 10 to the 8th power. How many Social Security numbers are available for each person? So in reality, everyone only gets one Social Security number in the United States, but they're saying that there's so many of them that if they did give them out to everybody, how many numbers would everyone end up having? So we're going to solve a simpler problem for this one too, but which is bigger, 10 to the 9th power or 3 times 10 to the 8th power? Well, if we open them up into standard notation, 3 times 10 to the 8th power is we take this and add the 8 zeros to it, because the 8 tells us how many zeros are supposed to be in front of next to the 1. And we get 100 million, okay? We multiply that by 3 and we get 300 million. 10 to the 9th power has 9 zeros. That's a billion. So this is a larger number. So we know that if we try to solve a simpler problem, we'll use a bigger number for this 10 to the 9th power and a smaller number for that one. So let's say there's 100 numbers and 30 people, because they're only one place value apart from each other. So we could say 130 are our two numbers. See that? Well, if there's 100 numbers and 30 people, how many per person? We would divide, wouldn't we? We'd see how many times 30 could fit into 100 to figure out how many each would get. So we're going to divide 10 to the 9th power and 3 times 10 to the 8th power. See? All right, so we've got them written as a fraction because that's a little division problem, right? And 10 to the 9th power is the same thing as 1 times 10 to the 9th power because of identity property, but that helps us because now we can separate the multiplier, this 1 over 3, from the powers of 10, can't we? And the division property of inequality says that we could subtract this 8 from this 9. So we're going to get a 1, and we don't have to write the 1. We know there's just a 10 there. So we end up with 1/3, see, times 10. Now, there has to be one digit in front of the decimal point, and we've got a 0.33. So we need to move this decimal point back. And by moving it back, we're going to remove that 10. This 10 is going to go away because we've now put the decimal point there, see? So remember that scientific notation can have only one digit in front of the decimal point, and it has to have one digit in front of the decimal point, okay? So if it's a 10.3, we've got to move it in between the 1 and the 0, see? And if it's a 0.3, we have to move it behind the 3, okay? And if we're moving it forward this way, we need to multiply it by 10 now. And if we move it back this way, we're going to take it away. So if we got a 0.3 and there's no powers of 10 here, we can say times 10 to the -1, couldn't we? Because that would be pulling it back, see? All right, so that is scientific notation word problems. I hope these are helping you. I know scientific notation can be very confusing, but you don't want to move on to the next topic until you really understand this, because we're going to be doing exponents a lot coming up in the coming up chapters. So you might want to see these videos, and there's a link in this description of this video, okay? I hope that helps. See you next video. Bye.